Hello everyone. In this session, we will discuss about the base drive control techniques for a BJT. When we were discussing the switching characteristics of the BJT, we saw that the saturating charge and therefore the saturating time negatively impacts the switching speed of the transistor. And hence, we try to obtain some optimized designs so that we can produce a good base drive control for a BJT. The switching speed can be increased. Let us go to the base drive control here. The switching speed of a BJT can be increased by reducing the turn on and turn off times. The turn on time can be reduced by allowing the base current peaking during turn on, which results in a low forced beta at the beginning. After the device has been completely turned on, the forced beta can be increased to a sufficiently high value to maintain the transistor in the quasi-saturation region. Similarly, the turn off time can be reduced by reversing the base current and allowing the base current to peak during the turn off as well. A typical arrangement for the base drive current is shown here in this waveform. Now, some of the most commonly used techniques that provide an optimized base drive for the transistor are turn on control, turn off control, proportional base control, and finally anti-saturation control. Let us discuss each one of them in detail. Coming to the first one, which is the turn on control. The base current peaking can be provided by a circuit as shown here. When the input voltage is turned on from 0 to V1, the base current is limited by the resistor R1 only. Now that is because at the very beginning we assume the capacitor to be not charged to any value. That is, the voltage across the capacitor is 0. So at time t is equals to 0, when you apply the base voltage, the capacitor acts as a short circuit and the current always follows the path with the lowest resistance, and R2 is not considered at this particular stage. However, when the capacitor starts to slowly charge, the current starts to decrease because the overall voltage, overall resistance across the base steadily rises from R1 to R1 plus R2. That is why we will obtain a peak like this. So at time t is equals to 0, only R1 will be applicable, and that's why you will obtain the maximum base current at the BJT base. Now as the voltage across the capacitor rises, the base current steadily decreases, and at this stage the capacitor is completely charged and the current will be a steady state value. So there are two currents for this particular circuit at time t is equals to 0 and at time when the capacitor is fully charged. Now let us look at these equations. So the initial current at time t is equals to 0 is equal to, you simply have to apply the KVL here. It is initial current is equal to V1, which is the applied voltage. This is V1 minus of the base emitter voltage of the transistor divided by R1, because the capacitor is currently shorted and R2 doesn't come into picture. Now when the capacitor is fully charged, R2 does come into picture and the final base current is given by V1 minus VBE divided by R1 plus R2. So now that we are taking into consideration the capacitor charging and discharging, it is very important that we must note what is the final capacitor value, or in simple words, what is the maximum capacitor voltage that can be applicable here. Now that is simply calculated by using this equation. The capacitor voltage is approximately equal to the input voltage multiplied by R2 divided by R1 plus R2. We have simply applied a voltage divider formula. Also, the charging time constant of the capacitor is given by R into C. But for the capacitor, since R1 and R2 are in parallel, R is simply the parallel combination, the equivalent resistance of two resistances R1 and R2 in parallel multiplied by C1. Once the input voltage VB becomes 0, the base emitter junction is reverse biased and the capacitor discharges through the resistor R2. Now the discharging time constant is simply given by R2 into C, because the capacitor, once the input voltage is removed, only discharges through R2. That is why the discharging time constant is R2 into C. Now to allow sufficient charging and discharging times, the width of the base pulse must be T1 greater than or equal to 5 times the value of tau 1, and a similar approximation is also applicable for T2, which is again greater than or equal to 5 times the value of tau 2. Now, one of the interesting facts about this particular circuitry is that it provides both turn on and turn off control, but it only provides equal values for both turn on and turn off. In order to obtain different turn on and turn off times, you should go for a small difference in the overall circuitry built. First, let us analyze how the same circuit is applicable for turn off control also. When the input voltage is changed from plus V1 to minus V2, the capacitor voltage is added directly to minus V2 across the transistor. So now the transistor sees two voltages. One is minus V2 across the base and another one is the capacitor voltage. This will provide a base current peaking as we have indicated in this particular diagram. Now as the capacitor C1 slowly discharges, the discharge current or the current here slowly reduces to 0, and when the current reduces to 0, the transistor is said to be in the off state. So this circuit can be used, as I already have said, for both turn on and turn off control. However, if you want different turn on and turn off characteristics, then you can use this approach. This once again a very similar circuitry, but the diode D1 here differentiates between positive voltage across the base and negative voltage. Now when positive voltage is applied across the base, diode D1 is forward biased, and the overall current is simply an approximation of all the elements that is used across the base. But when the input voltage is negative, that is minus V2, diode D1 is reverse biased, and only these elements R1, R3, C2 and R4 will be taken for approximating the value of tau 2. Therefore, you will obtain a different turn on and turn off times using this circuitry. The third technique that is used for providing base drive control for a BJT is called as proportional base control technique. This type of control has advantages over the constant drive circuits in which the load doesn't vary. If the collector current changes due to change in load demand, the base drive current is changed in proportion to the collector current, and it is an advantage of this particular technique. And a very simple arrangement for providing proportional base drive control is provided in this diagram. Let's understand how the operation of this circuit goes. When switch S1 is turned on, a pulse current of short duration would flow through the base of transistor Q1. Obviously, we have to understand the transistor operation. And the Q1 is turned on and goes into saturation. Once the collector current rises, a corresponding base current is induced due to the transformer action. Well, let us understand how this happens. Now, when you close the switch, a small input pulse voltage will create a current to flow across the N3, which will induce some voltage across N1, and this voltage is used to send the transistor into saturation. Now, when the transistor turns on, there will be a collector current which flows through N2, and this N2 has mutual induction or is attached with N3. So therefore what happens is, when there is a current flows across N2, it will create a current across N3, which in turn will create a current across N1, and therefore the transistor continues to be in the on state. One of the advantages, as we already have said, is when there is a change in load current, there will be a change in the collector current, which will change the value of the current flowing through N3, and there will once again be a change across the base current. So this particular technique has advantages over constant drive techniques. Now coming back to the operation, The transistor, when the collector current rises, will latch on to itself and now the S1 can be turned off. The turns ratio is given by N2 divided by N1, which is equal to the collector current divided by the base current, which is equal to the current gain beta. Now, for the proper operation of the circuit, the magnetizing current, which must be smaller than the collector current, should be as small as possible. The switch S1 can be implemented by a small signals transistor, and additional arrangements are necessary to discharge the capacitor C1 and reset the transformer core during the turn off of the power transistor. So this is about the proportional base drive control. Now coming to the last technique in line, which is the anti-saturation control. If the transistor is driven hard, the storage time, which is proportional to the base current, increases and the switching speed is reduced. The storage time can be reduced by operating the transistor in soft saturation rather than hard saturation. This can be accomplished by clamping the collector emitter voltage to a predetermined level, and the collector current then is given by collector voltage minus of VCM divided by RC, where VCM is the clamping voltage and the clamping voltage must be greater than VCE sat. A typical circuit that provides this operation, which is also called as a collector clamp circuit, is given here. The base current, which is adequate to drive the transistor hard, can be found by applying a simple KVL to this circuitry. Now when you apply the KVL, what you will get? IB is equal to I1. Please note, IB is equals to I1 equals to the base voltage minus the voltage across the diode D1 minus the voltage across the base emitter terminals of the BJT whole divided by the resistor RB. So that is what is given here. IB is equals to I1 equals to VB minus VD1 minus VB by RB. So since IB and IC are related by beta, the corresponding collector current, which is equal to IL, is given by beta RB. Now let us understand this is only when the collector has not yet clamped. Okay, the collector gets clamped when the diode D2 is turned on. Let us understand. It will come in the later part of the discussion. Now after the collector current rises, the transistor is turned on and the clamping takes place. And when the clamping takes place, the overall voltage across the collector to emitter, okay, now we are looking into these two terminals. The overall voltage across the collector to emitter is given by VBE plus VD1 minus VD2. So we have used this path for understanding the overall voltage across the collector to emitter. Okay, and the load current now is not equal to IC. When the clamping takes place, IC is not equal to IL. Without clamping, IC and IL are equal. So please note the clamping takes place, I already have said, when the diode D2 turns on, and when the diode D2 turns on, IC is not equal to IL. Please remember that. So when the clamping does take place, the load current IL is given by VCC minus of VCE divided by RC. Okay, let us write it down. Where is that? Yeah, IL is equals to VCC minus VCE divided by RC. But in the previous equation, we wrote an expression for VCE, correct? Which is equal to VBE plus VD1 minus VD2. So we will substitute this into this part to obtain a new equation. So let us remember this equation 9 is very, very important. Right. After this, the collector current with clamping becomes IC equal to beta IB, which is equal to beta into what is IB. Now the expression for IB changes because now the diode D2 is turned on. So IB is equal to I1 minus I2. So what is I2? I2 is equals to IC minus IL. So therefore IB is equal to I1 minus IC minus IL. We have written it here. So I1 minus IC minus of minus IL becomes plus IL. Okay. So after a little simplification, because IC is nothing but beta IB and all, and beta is IB is then related to the load current, we simplify this equation to get beta divided by 1 plus beta multiplied by I1 plus IL. Okay. So I1, you have to remember, is the base current. Please do not misunderstand. And that is what actually we have done in order to turn IC into IB. Okay, right. Now for the clamping operation to be successful, the voltage across the diode D1 must be greater than the voltage across diode D2. And this can be accomplished by connecting two or more diodes in place of one single diode. Also, the resistance RC should satisfy the condition given by beta IB must be greater than IL. What is beta IB? Nothing but IC. So, IC should be greater than IL for the clamping operation to be successful. So, now what I do, in the previous expression, I have written an expression for IL. Okay. So, I will take IL equal to VCC minus VB minus VD1 plus VD2 whole divided by RC, and I will substitute into this equation. And since we have a denominator given by RC, let me take it to the LHS. So RC here, which was at the denominator, is taken to the LHS, and the remaining part of the IL is written here. Okay. So this is what is the expression that is very, very necessary for a successful clamping operation. Now, to conclude, the clamping action results in a reduced collector current and almost elimination of the storage time. At the same time, a fast turn on is accomplished. However, due to increased collector to emitter voltage, the on-state power dissipation in the transistor is increased, whereas the switching power loss will be decreased. So that is about the different base drive control techniques of a BJT. Thank you.